Welcome to Calculus. Today we will investigate more optimization questions. We'll look at two examples today. We'll start with a similar scenario to what we saw with our first set of optimization examples. Here a farmer wants to enclose 600 square meters of land in a rectangular plot and then divide it into two plots with a fence parallel to one of the sides. Our task is to find what are the dimensions of the rectangular plot that require the least amount of fencing. So anytime you see this least or greatest, really that tells you you're dealing with the optimization question. So we'll start off by drawing a diagram. So similar to what we saw in a previous example, we're beginning with a rectangular piece of ground where in this case, it's just a third piece of fence. So not necessarily dividing it exactly in two, but parallel to two of the others. Now, here I don't know information about the linear fencing, but I do know information about the area. And so as I start, I want to label these three parallel pieces just X. They're all the same length. And then really the only information that I have additionally is that the area of this plot of ground, both pieces, is 600 meters. So if I think about if this length is X and the total area is 600, I could define the width as 600 over X, because area would be equal to length times width. So width itself is area divided by length. At that point, I want to set up an equation that really describes for me the perimeter of this fence. In fact, I want to set it up for the total length of fencing, because I got to take into account this middle piece, which wouldn't show up normally in the perimeter, but I do have to account for it since I'm using it with some of my fence. So the total length of fencing is going to be equal to 600 over X, but I've got two of those, the upper piece and the lower piece. So I'm going to multiply by 2. And I've also got 3 of these vertical pieces, so 3X. And then I want to just take the kind of simplify this function. So I'll just call it L is equal to 1,200 over X plus 3X. So at that point, I've got a function that would represent the length of fencing that I need in terms of this X. And so at this point, what I want to do is enter into the calculus part of this question, which is finding the optimization. I want to take the derivative of the length function. So that's going to be, if I consider that this is, first term is equivalent to 1,200 times x to the power of negative 1, the derivative of that is negative 1 times 1,200. And then over x squared plus 3. And so my derivative function is going to be negative 1,200 over x squared plus 3. And then I want to set that equal to 0, because again, I'm interested in either a relative maximum or a relative minimum. So then I want to solve this. So I'll start by subtracting 3 from both sides. And that'll give me negative 1,200 over x squared equals negative 3. To cancel the denominator x squared, I can multiply both sides. And that'll give me negative 1,200 equals negative 3x squared. Trying to isolate the x squared so that I can take square root. So I got to divide negative 3 from both sides. And what that gives me is negative 1,200 divided by negative 3 is 400 equals x squared. And then to finalize there, I just want to take square root of both sides. And we get that x equals plus or minus 20. We'll throw out the minus version since we're talking about length or distance. It's got to be positive. And so what we see here is that our dimensions are going to be 20 meters. That's my x. And then the upper part and the lower part are going to be 600 divided by 20, which is going to be 30. And that would minimize the amount of fencing that I would have to use to create a plot of ground that would have area of 600 square meters. Let's take a look at a second example that involves intensity of light. Here we're told that the intensity of illumination at a point varies inversely as the square of the distance between the point and the light source. Two lights, one having intensity 8 times that of the other, are 6 meters apart. We're going to try to answer the question, at what point between the two lights is the total illumination least? So let's draw a diagram just to represent these two lights. So I've got one light that is brighter than the other. In fact, 8 times as bright as the other. So I'll draw that one, and then another light that's significantly less bright, but still illuminating. And we're interested in a point between them at a location where the intensity from both lights would be at a minimum. Now we are told as well that this total distance between the two lights is 6 meters. So again, we want to kind of start labeling some stuff. I do know that the first light is 8 times as bright as the other one. We are interested in distances, so I'm going to call the distance from the brighter light to the point x. Now, if the total distance is 6 meters, from the point to the dimmer light would be 6 minus x. And at that point, what we want to do is create an equation for these. So I'm going to start off by calling, let's start with the intensity of illumination from the less bright light. So I'm just going to call it I, is going to be inversely proportional. So inversely means I've got a fraction, 1 over the square of the distance. So the distance is 6 minus x. And I've got to square that. So that's now set up just according to the way that it's presented in that first sentence. The intensity of illumination at a point varies inversely. So I got my fraction as the square of the distance between the point and the light source. Now I want to do something similar for this other x, but I'm just going to keep in mind it's 8 times the other intensity. So basically what I need to do is include an 8 in my numerator over x squared. Now, I want to set up the total intensity. So the total intensity is really just the two added up. So it's going to be 8 over x squared, that's the intensity of light from the brighter light, plus 1 over 6 minus x squared. And at this point, I'm interested now in the point that's going to get the least amount of illumination. So that's where I'm going to start to use differentiation. I want to find the optimal, either the max or the min. In this case, probably the minimum. So I'm going to find the derivative of the intensity equation we just wrote. So for this first one, I'm going to treat both of these like negative powers, 8x to the power of -2. That's really what I'm going to consider here. So that's going to be 8 times -2 over x cubed plus, this I'll treat as 6 minus x to the power of -2 again, just to help with the derivative. So that's 1 times -2 over 6 minus x to the power of 3. But then I have to take derivative of the interior, so that's going to be -1. And that'll set in the numerator. So for my function, I'm going to have -16 over x cubed. My double negative will cancel out, plus 2 over 6 minus x cubed. And that I want to set equal to 0. Now, in our previous examples, we used algebraic equation solving techniques. We could do that here as well, but I'd have to get the denominators the same, combine both fractions into one fraction, take the numerator, set equal to 0, and solve. That's a lot of algebraic steps. So just to show again what other tools we've got in our mathematical toolbox, I'm going to go over to the graphing calculator, and I'm going to plug that derivative function in just as we wrote it. So -16 over x cubed plus 2 over 6 minus x cubed. And it's a lot easier just to read off of the graph where it equals 0. So I see it's got an x-intercept there at 4. There is a horizontal asymptote that runs through this function on the x-axis. So the left side is not going to intersect the x-axis, neither is the right side. So we just have this one value, that middle part of the rational function at 4. And that tells us the information we need. So we're just going to go back here. From the graph, we get the solution x equals 4. And I should just write that. This is a graphical solution using x-intercepts. And that'll allow us to answer this question. So just to remember, what are we trying to answer? We're trying to say at what point between the two lights is the total illumination the least, the smallest. So if I put in my value of 4 here, that means the point is 4 meters from the brighter light or 6 minus 4 or 2 meters from the less bright light. And we'll box that. That is our answer for this question. Thank you for joining for these 2 examples of additional optimization questions. See you soon.